Hello, my name is Nai Lot, and I'm a second-year graduate student working with Dr. Sishu Chen. I've been spending a lot of time with mass spectrometers lately, mainly focusing on untargeted metabolomics through an LCMS, but I've also been learning some MALDI applications and been doing some proteomics. I've put together this video to show off the mass spectrometers that are in ICBR currently. Hopefully this will provide some visual background to your lecture and help show how mass spectrometers actually work without providing an overwhelming amount of detail. As you may know, mass spectrometers fundamentally work by manipulating and detecting ions, ultimately recording an ion's mass-to-charge ratio. Applying mass spectrometry techniques in conjunction with liquid or gas chromatography or a MALDI system can allow a scientist to measure complex biological samples, such as a peptide mixture or a metabolite extract. With a well-informed experimental design, mass spectrometry setup, and appropriate data analysis, many biological questions can be unraveled. This is a mass spectrometer with a transparent body in Dr. Chen's lab. It's a comparably simple model used for teaching. Most mass spectrometry components need to be kept in a high vacuum to allow uninterrupted ion flight. Here you can see the turbo pump, which is then connected to an auxiliary rotary pump, and combined they can reach a near perfect vacuum. On the front we have an inlet. I believe in this case it's an ESI source hooked up to an HPLC. ESI, or electrospray ionization, is a common soft ionization method for liquids. ESI relies on a high voltage power supply in conjunction with a stream of dry gas. The droplets of solvent build up a charge while they evaporate in the hot gas until that charge becomes too great and they explode into a cloud of ions. The ions are then sucked into this quadrupole mass filter, which can restrict ions to a certain range. The subsequent hexapole ion guide directs ions then into another quadrupole, which is in this case a mass analyzer, and then through another ion guide into a detector. This relatively simple system can fit comfortably with the accompanying LC system on a tabletop. Building on this system, hybrid mass spectrometers combine multiple mass analyzers, fragmentation systems, ion separation methods, and different mass detection methods. The various hybrid mass spectrometry systems are designed for different applications, such as untargeted versus targeted workflows, and have different qualities such as extremely high resolution or mass accuracy. For example, this older but still highly useful 4000 Q-trap, which happens to be under repair right now, so I don't have a perfect picture. But anyway, it's a triple quadrupole with a linear ion trap. It is an LC-MS system and is typically used for targeted metabolomics applications. This system here is an Orbitrap fusion. It uses a linear ion trap and an Orbitrap mass analyzer to separate ions and increase resolution. It is regularly used for untargeted metabolomics as well as for proteomics. The last mass spec I'll feature in this video is the one I've been working with the most in my research, the timsTOF Flex. It is the latest cutting-edge hybrid mass spec system from Bruker and was designed to perform well in many different applications requiring an untargeted approach and high resolution. As you can see, it is a large box that contains a great deal of different components. For ionization, there is an ESI source visible here, and with the source removed, the opening for the glass capillary that carries the ions further into the system is visible. There is also a MALDI source with the opening slot here, and its neodymium YAG laser being this very large box here. The laser is designed to have a burn spot as low as 5 microns, making the system potentially viable for single-cell metabolomics imaging. Further in, we have the TIMS, or trapped ion mobility cell. This system is what makes the timsTOF special, as it separates ions based on their physical, dimensional structure by driving them upwind, so to speak, against an electric current using gas flow. This can allow the separation of highly similar chemical isoforms that resist separation by chromatography. The next visible component is the quadrupole mass filter, the tips of which are visible here. Ions are then fragmented in the collision cell before being sent to the orthogonal accelerator, which is the beginning of the time-of-flight detector. This launches ions to the top of the column, which are then reflected back to a detector at the base. The acceleration of the ions can be calculated from the electric field applied, with heavier ions achieving a lower velocity. The time it takes for these ions to travel through the system is then used to determine mass over charge. I hope this video was interesting and informative. Mass spectrometry is a powerful but complex tool, and a little understanding of its intricacies can go a long way in designing an experiment. With that, I'll end with a neat little video of the MALDI laser sampling a leaf, and if you have any questions, you know who to ask.